We're going to look at two example problems with calorimetry. And the root word calor means heat. So the word calorimetry means to measure. That's what metry means, heat. So we're going to be measuring the heat flow from one place to another. When I'm dealing with heat flow, I find that pictures and thinking about what's in my system and not in my system really helps me think about the problem. So I'm going to start by doing a picture. So in this problem, which comes from your textbook, page 262, we've got a block of copper of unknown mass that has an initial temperature of 65.4. So I'm going to draw a little picture of my copper, and its temperature is 65.4 degrees. And it says the copper is immersed in a beaker, so I need a beaker, and the copper is going to go into it. And that beaker contains water, and it has 95.7 grams of water, and the temperature of the water is 22.7 degrees Celsius. So it says when the two substances reach thermal equilibrium. Thermal equilibrium means that they've reached the same temperature. The final temperature is 24.2 degrees Celsius. So I know that for the system at the end, the final temperature of both of them together is going to be 24.2 degrees Celsius. And we are trying to figure out the mass of the copper block. So I like to draw a picture to organize what I know. I also like to think about a system picture. So if copper is my system and water is the surroundings, then the energy is going to flow from the hotter item to the cooler item. So Q is going to go from the copper to the water. So I can use that to write my energy conservation equation. The Q of the copper that is lost, so that gets a negative sign, is equal to the Q, the energy gained by the water. And in this case, copper is undergoing a temperature change. So its Q is mc delta T. And all this would refer to the copper. And water is also undergoing a temperature change. So to calculate the amount of energy transferred into the water, we would calculate mc delta T, but this would all be for the water. So I'm going to substitute in what I know. I do not know the mass of copper. That's what I'm trying to figure out. I'm guessing that I can look up the heat capacity of copper. Usually on an AP problem, you would just be provided with it. But I can look it up, and I found that the heat capacity of copper, according to a table in our textbook, is 0.385 joules per gram degree Celsius. And I also know that the heat capacity for water is 4.18 joules per gram degrees Celsius. So the heat capacity of copper I'm going to use here for C, 0.385. The temperature change of copper, its final temperature is 24.2. Its initial temperature was 65.4. For water, the mass of water I'm given as 95.7. The heat capacity of water is 4.18, and the temperature change of water ended at 24.2 degrees, and it started at 22.7 degrees. So I've got a lot of math here that I'm going to do and combine a bunch of numbers. And when I do that math, on this side I got 15.862 times the mass of copper is equal to 600. So divide both sides by the 15.862, and I found that the mass of copper was equal to 37.8 grams. It's also worth pointing out some important concepts here. In this case, notice we had a very big temperature change for the copper, from 65 all the way to 24, versus a very small change in temperature for the water. And that's going to be in part due to two things. One, we've got about 3 times the mass of water as we do the mass of copper, and also the heat capacity of water is more than 10 times the heat capacity of the copper. So between that, I'm expecting the temperature change for the copper to be almost 40 times, or about 40 times the temperature change of the water, and it is. We're going to look at one more example, but this time instead of 2 different things both changing temperature, we're going to have something changing temperature and something else going through a reaction. So this is another way to do calorimetry, where you either have something dissolving or something going through a reaction, and you use the temperature change often of the water to determine how much energy was released or added into the reaction. So in this problem, we've got 50 milliliters of a 0.1 milliliters silver nitrate combined with 50 milliliters of 0.1 molar hydrochloric acid in a coffee cup calorimeter. A coffee cup calorimeter, if you've never heard that term before, it actually means exactly what it sounds like. If you take 2 styrofoam coffee cups and nest them inside of one another, they're actually pretty good at insulating, and so often in chemistry labs we will use that as our calorimeter, a calorimeter just being a device that is used to measure heat, because the insulation keeps most of the heat inside what you're studying, what you're measuring. So we're going to draw our little picture here. We've got a cup, and into that cup we are going to put 50 milliliters of 0.1 molar. Oh, just realized there's a typo in my slide. This should be 0.1 molar, like I said out loud, not 0.1 milliliters. So 0.1 molar silver nitrate. And also we're going to put in 50 milliliters of 0.1 molar hydrochloric acid. And so in total, in this solution, once we mix them both together in this container, we're going to have a total of 100 milliliters of solution, which is mostly water with a little bit of hydrochloric acid and silver nitrate dissolved in it. And it says that the solution changes from a temperature of 23.4 degrees Celsius to 24.21 degrees Celsius, and it says calculate the enthalpy of reaction. So when I've got a temperature change and it's related to either a reaction or a dissolving process, thinking about the system is a little bit more sophisticated. We want to think about our system as the chemicals that are reacting. So in this case, the silver nitrate and the hydrochloric acid, and even though they are dissolved in water, the water is also really the surroundings. The water is going to heat up or cool down, in this case it's heat up, based on the energy coming out of, or if it was cooling down, going into the chemicals and their bonds as bonds are being broken and formed. So the chemicals are our system, and the water and its temperature change records what's happening to the surroundings. So I need to think about energy conservation here. And I'm going to write my energy conservation equation as the energy lost by the chemicals, or the loss by the chemicals in the reaction, is equal to the energy gained by the water. And so I'm going to calculate the Q of the chemicals. I don't know anything about them yet, by first figuring out the Q of the water, which is a temperature change. It'll be MC delta T. I am going to make an assumption that because solutions are primarily water, and water has a density of 1 gram for every milliliter, that the mass of our water is going to be 100 grams. And I know the heat capacity of water is 4.18 joules for 1 gram to go up 1 degree Celsius. And our temperature change is 24.21 minus 23.4. So I can figure out the heat gained by the water, and that's going to be equal to the energy lost by the chemicals. So let's do that calculation. And when I solve for the Q of the chemicals in the chemical reaction, I get that the Q of the chemicals is negative 338 0.5 joules. And the negative should make sense because if the water's heating up, it indicates that energy left the chemicals and that this is an exothermic reaction, and exothermic reactions have negative signs. Now we are not done yet because it's asking us to calculate the enthalpy of reaction. Enthalpies are usually given with units of kilojoules per mole of reaction. So we're going to have to make two adjustments here to our number. We have the number of joules. We need to figure out how many moles generated this many joules. So coming back up to the problem and the numbers that we were given, we've got 50 milliliters and 0.1 mole. I remember that if I know molarity and volume, that I can multiply them together to get moles, but I need to use volume in liters because molarity is defined in terms of liters. So that means I have 0.1 times 0.05, which is 0.005 moles of AgNO3. And I also have 0.1 times 0.05, which is 0.005 moles of HCl. And I should also take note of the balanced chemical reaction. I have 0.005 moles of this and 0.005 moles of this. And since they react in a 1-to-1 mole ratio, we'll basically consume 0.005 moles of both of these. So to figure out the heat of reaction, I'm going to divide by 0.005 moles, because 0.005 moles is what's generating negative 338.5 joules. I also want to convert joules to kilojoules, so there are 1,000 joules in 1 kilojoule. So when I make those two adjustments, I find that there are negative 67.7 kilojoules for every 1 mole of reaction. So there's our heat of reaction in terms of 1 mole of reaction. The very common type of problem for an AP test to ask in the free response section. So I strongly urge you to do a lot of practice with this and make sure you really understand it. We got a follow-up question that's very similar to follow-up questions that tend to be asked in the free response question. So we are making a big assumption when we think about this up here, when we write our energy conservation equation. We are assuming that all of the energy lost by the reaction goes into the water. In reality, while a lot of it works, we are using a coffee cup calorimeter here, some of the energy is actually going not into the water, but into the air and the other surroundings. Maybe it's heating up the styrofoam cup a little bit. It's just going other places. And so, if that's the case, then our energy conservation equation would become energy lost by the chemicals is going to be equal to both the energy gained by the water and some energy gained by like the air and the other surroundings. So that means if some energy went to the air, then we are underestimating this Q chemical because we're only able to measure the amount of energy that went to the water. So this means that the Q chemical will be smaller than it actually is because we aren't accounting for this stuff here. Therefore, because the enthalpy of reaction is directly based on the chemical energy lost by the chemicals and gained by the water, then we would underestimate the enthalpy of reaction. So we've seen 2 examples of calorimetry. This would be some very important problems for you to practice on your own, and homework 4B will give you a lot of opportunity to do just that. Feel free to refer back to these examples as you need.